Today we are going to learn about the reactions involving the condensed phases. Okay, so first of all, we need to know what are these condensed phases and how can you relate them with your thermodynamic properties. Okay, so understanding the condensed phases. Condensed phases are those phases which has a predefined volume. Okay, like your liquid state or your solid state, they have a confined volume, and all the thermodynamic properties are related to these confined volume. Okay, so these are your condensed phases. Okay, now let us understand that how this condensed phases has how can you understand about the thermodynamics or the reactions of your condensed phases. Okay, so basically there are two different kinds of reactions that are going to we are going to study in this part. That is your oxide formation. That is, if your oxide is in solid or the liquid phase, then how will your reaction be affecting? Similarly, the relation between your sulfide, that is SO2, and your oxygen relation. Okay, based upon this, based upon the relation between your sulfur dioxide and oxygen, you obtain your predominance area diagram, right? Similarly, the stability of an oxide is decided by your Ellingham diagram. Okay, so mainly in our today's lecture, we are going to study about your Ellingham diagram, and we will see about different observations related to your Ellingham diagram. Okay. All right. So as I told you that condensed phases are basically those phases. Condensed phases are those phases which have predefined volume. Okay. And we know these cases, which are these condensed phases, basically your liquid phase or the solid phase. They have a fixed volume or a predefined volume or a confined volume, and because of that we call them as the condensed phases. Okay, so all those reactions in which there is an involvement of these condensed phases comes under the category of your reactions containing or involving your condensed phases. Okay, so let us understand. Basically, as I told you, that will be focusing our study based upon two different kinds of reactions, that is your involving your metal oxide, and similarly the reactions involving your metal sulfide. Okay, so as per your oxide reaction, the reaction containing your metal oxide, you obtain your Ellingham diagram. Okay, similarly the reactions involving your sulfides, your metal sulfides, and their stability, we basically obtain your predominance area diagram. Okay, so let us start with your Ellingham diagram. Let us see what is your Ellingham diagram and what are different observations for your Ellingham diagram. Okay, so your very first part, what you need to understand, that this Ellingham diagram, it basically tells us about the free energy relation with your temperature, right? So this is nothing but your delta G versus T curve. Okay, so if I draw your Ellingham diagram, it is nothing but your delta G versus T curve. Okay, where delta G is what? Nothing but the change in the free energy of the reaction, where T is your temperature, right? So the curve drawn between your delta G versus T will give you the Ellingham diagram. Okay, now what you need to understand, that this Ellingham diagram is basically used in order to determine which oxide is more stable. Okay, mainly those oxide lines which are present at the bottommost part of your Ellingham diagram are much more stable as compared to the above part or the above oxide. Okay, and similarly those metals which are present at the bottom line, are at the bottommost positions of your Ellingham diagram, they form your most stable oxide, right? So definitely these metals can easily reduce the above oxides in order to form the stable metal oxide. Okay, so it not only just tells us about the stability of the oxide, but it also tells us that which metal is capable of reducing the other metal oxide. Okay, now what you need to know. Okay, so if I give you in the bullet point, Ellingham diagram is used to calculate the stability of the oxide. Okay, along with this, we also obtain which metal is capable, which metal is capable of reducing other metal oxide, of reducing other metal oxide. Okay, so okay, so as I was saying that your Ellingham diagram, it is basically made for, we basically study for your oxide part, but apart from your oxide, your Ellingham diagram is also made for your sulfides, okay, and fluoride. So similarly, in these cases also, they tell us about the stability of different sulfides and fluorides respectively. Okay. All right. So let us learn how this Ellingham diagram is generated and how can you say that your delta G versus T curve is accurate. Okay. So basically, if I take a reaction, let us understand with the help of a reaction, it will be much more simpler in that case, right? So if I take a reaction, say M plus O2 gives MO2. Okay, your M is your solid state, oxygen is definitely in your gaseous state, and the oxide that we obtained is also in the solid state. Okay, so if I write what is my delta G for this reaction, my delta G can be written in terms of your enthalpy and entropy value, right? So delta G is nothing but delta H minus T delta S. Okay, so where delta H is what? Basically the change in the enthalpy of the reaction. If this delta H is positive in nature, that is that we obtain a positive value, then we can say that this reaction is actually endothermic in nature, right? What do you mean by endothermic reaction? Basically you need to supply sufficient amount of energy in order to proceed this reaction in the forward direction. Okay, similarly if your delta H is negative, so if delta H is positive, it is an endothermic reaction. Okay. Similarly, if your delta H is negative, it is known as your exothermic reaction. That is, the heat is being liberated from the reaction, if from the system, if this reaction occurs. Okay. So such a kind of a reactions are basically known as your exothermic reaction. Okay. Now, if I calculate these values, I'm basically interested in my Ellingham diagram, right? What is your Ellingham diagram? It is nothing but delta G versus T curve. Okay. So from this line, from this expression, that is delta G is equal to delta H minus T delta S, I can say that my delta G is basically equal to minus T delta S plus delta H. Okay. So from here, the slope of my line, this is basically the equation of a straight line, right? That is y equal to mx plus c. Okay. Where m, or the slope of this straight line, is nothing but the negative of the change in the entropy, right? Whereas the intercept is basically given as your delta H, or the change in the enthalpy of the reaction. Okay. Now, considering that this reaction is going in the forward direction, okay, so if the reaction is going in the forward direction, then we will take your delta G to be negative value, right? That is, the reaction is feasible. Okay, so if the reaction is going in the forward direction, delta G is negative, right? If the reaction is feasible, your delta G will be negative. Okay, so if your delta G is negative, then definitely I can relate it with your delta G versus temperature curve, right? If your delta G is negative, okay, so basically inside your Ellingham diagram, your delta G is basically represented over your y-axis, right? Whereas temperature is represented over your x-axis, and your temperature will always be positive, right? So out of the four quadrant, this is your positive x, this is your negative x, this is your positive y, and this is your negative y. Okay, so this is your first quadrant, your second quadrant, your third quadrant, and your fourth quadrant. Okay, so out of the four quadrant, or based upon the two axes, your x and y, we basically see that your Ellingham diagram is a diagram that is drawn in your fourth axis or the fourth quadrant. Okay, what is your fourth quadrant? Basically, your y axis is basically negative in nature. That is, your delta G is negative. Okay, whereas your temperature is positive. Okay, so basically you obtain your Ellingham diagram in the fourth quadrant. Okay, all right, so let us see different observations related to your Ellingham diagram, and how can you relate this Ellingham diagram with your thermodynamic part. Okay, all right, so let us start with your observation. Basically, there are five major observations that are important for us to understand. Basically, we have five major observations. All right, so your observation number one. Now, as per the observation number one, if you practically see your Ellingham diagram, you will observe that most of the lines are going in the upward direction, right? Most of the lines, most of the oxide lines I'm talking about, most of the oxide lines go in the upward direction. Okay? Now, how is that so? And why is this happening? Basically, that is what we are going to learn here. Okay. So if I take an example, in my previous reaction, I told that I took a metal that is solid in nature and combined it with oxygen, that is your gaseous phase, right? And it gave me the metal oxide that is also in the gaseous phase. Okay, so if I ask you that what is the change in the entropy of the reaction, basically the slope is depending upon the change in the entropy of the reaction, right? And depending upon the slope, whether it is a positive slope or a negative slope, the line or the oxide line that we are drawing inside your Ellingham diagram, it will go either in the upward direction or in the downward direction. Okay, so first of all, we need to calculate what is the slope of this reaction. Okay, and in order to understand that what is the slope, we need to calculate what is the change in the entropy of this reaction. Okay, so as per this reaction, I can say that the change in entropy, now entropy is also a state function, right? So the change in entropy of the reaction is nothing but the entropy of your product, sum of the entropies of your product minus sum of the entropies of your reactant. Okay, since you have two reactant and you have only a single product, so definitely we are talking in terms of your sum of the entropies of your product minus sum of the entropies of your reactant. Okay, all right, I mistakenly took this metal oxide to be in the gaseous state. It is actually in the solid state, right? Your metal oxide, most of the metal oxides are in the solid state, so we'll be considering the general case, that is your metal oxide is in the solid state. Okay, so if I calculate what is the change in entropy of this reaction, let us see what happens. Okay, so entropy of the product, so this is the entropy of your metal dioxide or MO2 minus entropy of your reactant, so this is the entropy of your metal plus the entropy of your oxygen. Okay, now we know that the entropy value, what is the relation between entropy for different phases? Basically, your gaseous phase, it is very much higher as compared to your liquid, as compared to your solid, right? And this relation is in such manner that if you compare your entropies of your gaseous phase, they are so much higher as compared to the entropy of the solid phase that you can actually ignore those values. Okay, you can actually ignore those values. For instance, if I just taking a random example, If I have my entropy as 1000 for your gaseous phase, then for your liquid, you will have the entropy in the terms of your 10 or the multiples of 10. Okay. Whereas for your solid, you will be having the entropy in the terms of your 0.1 or 0.000. Okay. So it is so less that you can actually ignore this value, or you can ignore the value of your entropy for the solid as compared to the entropies of your gaseous phase. Okay. All right. So now we know that this is your solid phase, this is your solid phase, and this is your gaseous phase, right? So if I calculate the change in the entropy of the reaction, this is what? This is nothing but the entropy of your solid phase, right? So I can directly ignore it and say that it is equal to zero. Similarly, the entropy of your pure metal is also equal to zero, as since it is also a solid phase, right? So your delta S reaction is nothing but minus of SO2, that is your gaseous phase, right? Now from here, what we observe, basically, the change in the entropy of your reaction is negative in nature, right? It is negative in nature. Whenever we are obtaining your metal oxide in the solid phase, your change in the entropy of the reaction will be negative in nature. Okay. Now, slope of this line or the oxide line, it is what? It is nothing but minus delta S, right? So this negative sign will combine with the entropy value of your oxygen of the gaseous phase, okay, and your slope will become positive. Okay. So once the slope becomes positive, this is the basic reason by most of the lines, or the oxide lines we are talking about, they go in the upward direction. Okay. Because the slope of these lines basically comes positive, and this is positive because the entropy itself is a negative value. Okay. So I can say most of the lines go upward. All right. So coming on to our observation number 2. What is your observation number 2? Okay. So if you look carefully inside your Ellingham diagram, you will find one line only, where which is an horizontal line, right? It is like close to being parallel to your x-axis or the temperature axis. Okay. Now, what happens in this case, and how can you say that it is parallel to your x-axis or the temperature axis? And what are these oxides and reactions that occur? Okay. So basically, in your observation number 2, if you find out this reaction inside this kind of a line inside your Ellingham diagram, so you can easily observe what is the relation or the reaction that is occurring over it. Okay. So this occurs for the reaction where your carbon combine with your oxygen to give a carbon dioxide. Okay, so your carbon is in solid state, oxygen is in gaseous state, and carbon dioxide is also in the gaseous phase. Okay. Now, if I calculate what is my change in the entropy of the reaction, this is what? This is nothing but the entropy of your product minus entropy of your reactant, right? So from here, we know that you have only one product, that is your carbon dioxide in the gaseous phase. So this is nothing but the entropy of your carbon dioxide. Now this is your gaseous phase. Please remember, this is your gaseous phase, so you cannot neglect this value. Okay, minus entropy of your carbon, which is in the solid state, plus the entropy of your oxygen, which is again in the gaseous phase. Okay, so I can easily ignore this entropy of your solid phase or the carbon when we are comparing in terms of your gaseous phase. Okay, now what you need to know, what you need to see over there, that the entropy values, they have a single mole of your carbon dioxide is produced by combining your 1 mole of oxygen with 1 mole of carbon, right? So overall I can say that all the moles, all the elements we are taking or considering for 1 mole of the component. Okay. Now in this case, since both carbon dioxide and your oxygen, they are in the gaseous phase, so their entropy value will be somewhat similar, right? Although if they are not equal because of the different atoms and atomic energies, but somewhat in the gaseous phase, the entropy value will be somewhat equal to, means it will be approximately equal. Okay. So from here, your delta S is nothing but S of carbon dioxide minus S of oxygen. Okay. And since both of them are in the gaseous phase and both of them are approximately equal, so from here you will obtain your delta S is approximately equal to 0. Okay. So that is the change in the entropy value, or the change in the entropy of the reaction for this kind of a reaction is basically equal to 0. Okay. And because of that, since the slope is 0, okay, delta S is what? Delta S is nothing but the slope, right? So if the slope is 0, I can say that this line basically is horizontal to the temperature axis. Okay. So this is your observation number 2, that your C plus O2 giving carbon dioxide. This line is basically horizontal to the temperature axis. Okay, or it is an horizontal line. All right, coming on to our next observation. Okay, so what is your third observation? Observation number 3. Now, as per our third observation, if you clearly watch your Ellingham diagram, you will find one line which is going in the downward direction. Okay. Now, how does this line goes in the downward direction, and what is the basis behind that? We are going to learn this. Okay. So basically, if you check this line, if you check over your Ellingham diagram, you will find that this is nothing but the reaction of your carbon plus oxygen given 2 carbon monoxide. Okay. Now again, in this case, you have 1 mole of your carbon, that is, sorry, 2 moles of your carbon, which is in the solid phase, right? Whereas 1 mole of your oxygen, which is in the gaseous phase, right? Similarly, you have 2 moles of your carbon monoxide, which is also again in the gaseous phase. Okay. So if I ask you to calculate what is the change in the entropy of this complete reaction, okay, so delta S reaction is nothing but the sum of the entropies of your product minus sum of the entropies of your reactant. Okay. So this is what in product side you have only one product, that is your carbon monoxide. Okay. So this is nothing but 2 into entropy of your carbon monoxide minus, okay, now again in terms of your reactant you can say 2 into entropy of your carbon plus 1 into entropy of your oxygen. Okay, now this is your solid state, this is your gaseous phase, and this is again your gaseous phase, right? So definitely, since it is a solid phase, so I can neglect this value or ignore this value, right? This will be nothing but equal to 0 as compared to your gaseous phases. Your entropies of your solid phases will be much lower, right? So I can easily drop this down, and we can compare your overall reaction or the direction of your oxide layer or oxide line based upon the entropy value or the change in the entropy of this reaction. Okay, or the gaseous phase basically. All right. Now, what you need to understand here is that basically you have 2 moles of your carbon monoxide. Okay. So, for instance, let us understand in terms of your example. Okay. So, if I say that my change in the entropy value, or sorry, the entropy of my carbon monoxide is somewhat equal to 1001. Okay. Whereas the entropy of my oxygen in the gaseous phase is approximately equal to 1000. These are your some hypothetical observations or hypothetical examples, you can say. Hypothetical. Okay. All right. So if I ask you that what will be the change in the overall entropy of the reaction? Okay. Now what you need to see that your carbon monoxide basically contains 2 moles. Okay, so you need to multiply with 2. Okay, whereas your oxygen, it is being utilized in a single, you can say only 1 mole of your oxygen is being utilized. Okay, so from here I can say that by entropy, the entropy of your product will be very much larger as compared to the entropy of your reactant, right? This is nothing but 2002, right? And if you subtract it with your initial condition, this is nothing but 1002. Okay, so this is actually 1002, which was far more than the value of your initial carbon monoxide. That is the entropy of your carbon monoxide. Okay, so definitely in this case I can say that the value or the delta S of the reaction, this will be actually a positive quantity. Okay, so from here I can say that delta S reaction is actually a positive quantity. Okay, and the reason behind it is that the entropy of your product is much higher as compared to the entropy of your reactant. Okay, so if your delta S of the reaction is basically positive, then your slope is what? Minus delta S, right? So this will be negative. Okay, so basically your slope has become negative, and because of that, this line basically goes in the downward direction. Okay, all right, so let us move on to our next observation, that is observation number 4. Okay, what is in this observation? It is actually quite important. Okay, so basically I told you that inside your Ellingham diagram that is drawn over your fourth quadrant, you will be obtaining your different oxide lines, right? And based upon the position of these oxide lines, whether they are close to the bottom of the Ellingham diagram or at much higher distances, you can determine which oxide will be much more stable, right? Now, what was seen during your Ellingham diagram, that after a certain specific temperature, the stability of the oxide basically changes. And why does that happen so? It's basically because of the intersecting of the two lines inside an Ellingham diagram. Okay. So our next observation of the observation number 4 is basically telling us about the intersecting lines of Ellingham diagram. Okay. So if I draw my Ellingham diagram, this is a general situation. This is a general format in which the Ellingham diagram is drawn. Okay. So your x-axis basically represents your temperature, and y-axis basically represents your delta G. Okay, so this is increasing in this order. Okay, it is increasing in this order, and your temperature is basically increasing according to your rightward direction. Okay, now what happens? Let us see. Basically, you have two different metal oxide lines. Okay, let me take two different reactions, and based upon that, we'll see what are these two different metal oxide lines and how they are intersecting at a particular temperature. Okay, so I take my first reaction as considering a hypothetical component A. When it combines with your oxygen, it gives your AO2. Okay, now again, this A is solid, oxygen is in gaseous phase, and AO2 is again solid in nature. Okay. Similarly, you have my second reaction, that is 2B plus oxygen gives 2BO. Okay. Again, these are your solid phases. Oxygen is definitely gaseous, and this BO is also solid phase. Okay. Now, what happens during the intersecting of the lines? That is what we are going to learn over. Okay. So let me take that there are two lines going in this manner. Okay, so basically the intersection occurs at this temperature. Okay, So your intersection basically occurs at a particular temperature. Let me call this temperature as T1. Okay. So if I say this line is basically my A in equilibrium with your AO2, whereas this line basically represents 2B in equilibrium with 2BO. Okay. Now, what do you observe in this condition? Basically, you have three reasons, right? One reason that is below your T1 temperature. Another reason is that at T1 temperature. And similarly, the third reason is where the temperature T1 is actually lower as compared to the initial condition, right? That is your temperature is higher than your T1 temperature. Okay. So what happens in this situation? We are going to learn about this. We are going to understand. Okay. Now, if I consider for my temperature less than my T1 temperature, for my temperature less than my T1 temperature. So this is the temperature I am talking about. Okay. So if I draw a straight line from this temperature axis, okay, we find that the free energy of A converting to AO2, free energy of A converting to AO2 is much higher. Okay. This free energy of A converting to AO2 is much lower, right? It is much lower as compared to the free energy of your B converting into BO. Okay, let me take this free energy values as your G1 and G2 respectively. Okay, so basically, at your temperature T, which is less than your T1 temperature, your metal oxide, that is AO2, is much more stable as compared to the other metal oxide, that is your BO. Okay, so if your metal oxide AO2 is more stable, then definitely the metal A can easily reduce the metal B of BO. Okay, it can easily reduce your metal BO, metal oxide BO. Okay, and form a more stable oxide. Okay, so basically, when the temperature is less than T1, your AO2, this line is stable, this oxide line is stable, and your A metal can reduce, your A metal can reduce the BO line. Okay, that is basically your B oxide. You can easily reduce your B oxide. Okay, and because of that, you obtain this is what, this is at the temperature which is less than your T1 temperature. Okay, similarly, if your temperature is basically equal to your T1 temperature, then definitely your AO2 and BO both are in equilibrium, right? So if both of them are in equilibrium, then definitely you cannot say whether the reaction will be going in the forward or the backward direction. Okay, whether your AO2 will be appearing next or your BO will be appearing next, you cannot determine that. Okay, similarly, if my temperature is greater than T1, okay, so if my temperature T is greater than T1, okay, now what you understand in this case is basically the free energy of your BO is lesser than the free energy of your AO2 in this case, right? So if the free energy of your BO is less than the free energy of your AO2, okay, the free energy of BO is basically less than the free energy of your AO2. This basically tells us that which phase will be more stable or which oxide will be much more stable, right? When the free energy or when the free energy of the material reduces down, then definitely that material becomes much more stable, right? So in this case, if the free energy of your BO is less than the free energy of your AO2, then definitely your BO is more stable in this case. Your BO is more stable in this case. Okay. Another thing that you need to understand that your metal B, okay, you have your metal B, it can easily reduce, can easily reduce your AO2 line or the AO2 axis. Okay. So your B metal, it can easily reduce your AO2 line. Okay. And this is what we learn in your intersection of your different lines inside your Ellingham diagram. Okay. So if I summarize everything, we have seen based upon this observation number 4 I am talking about. Okay. So basically, your free energy, whichever phase will be having a lower free energy, that will be more stable, right? Whichever phase is having a lower energy, that will be more stable. And this lower and the upper limits are basically decided after drawing this particular, okay, point of intersection, the two intersecting lines, at which position they intersect. Based upon that, we determine that what will happen in the condition when the temperature is less than your equilibrium temperature or intersection temperature, you can say. Okay. Similarly, what happens in the case when the temperature is greater than your intersection temperature? Okay. So we have discussed everything in this part. All right. So coming on to our fifth and the last observation. Okay. Now you must have seen in your Ellingham diagram, this is your delta G and this is your temperature, right? Many of the oxide lines, they grow at a particular temperature. Okay, they have their particular slope, and right at a certain temperature, okay, they has a sudden change in the slope. Okay, so if I'm talking about this condition, if I have my slope m1, okay, let me take this as A converting into AO2. Okay, in this case, initially I had my slope of the line as m1, and right after passing through the temperature of your T1, okay, let me take it as T2 so that it is not confused with your intersection temperature. Okay. Similarly, there will be a sudden jump in the slope of the line. Okay. Similarly, there could be another condition, right? There could be another condition where you must have observed a sudden drop inside the material. Okay. So it should have been going in this direction, but instead it went down in this direction. Okay. So again, I'm considering this time as my T3 time. Okay. So we will be seeing this observation number 5 one by one based upon the different cases. Okay. What happens in your case 1? This is your case 1 I'm talking about. Okay. Similarly, this is your case 2 which we are considering. Okay. All right. So let us see that how this slope of the line changes. Okay. All right. So if I have the reaction, where I have considered your reaction, right? Your A plus AO2, your A plus oxygen gives your AO2, right? So if I write down this reaction, A plus O2 gives AO2. Okay, so this is your solid phase, this is your gaseous phase, and this again is your solid phase. Okay. Now, what you need to understand that this change in the slope of the line at all of a sudden is basically due to the change in the phase transformation. Okay. Now this line, the slope of the line, it goes either in the upward direction or in the downward direction, depending upon the slope of this line. Right, the slope of this line, it will go either in the upward direction or the downward direction, depending upon the size, depending upon the side or the position where the phase transformation occurs. Okay. So considering that my melting point of A is lower than the melting point of my AO2. Okay. If the melting point of A is lower than the melting point of your AO2, what will happen after some time? Okay, I'm increasing the temperature continuously. Okay, so I'm increasing the temperature. Let us see what will happen. Okay, so basically, since the melting temperature of A is much lower as compared to the melting temperature of your AO2, so there will be transformation at your reactant side, right? Your A will convert into liquid plus oxygen, having your gaseous phase, whereas your AO2 will still remain in your solid phase. Okay. Now, what will happen? Let us understand. Basically, if I ask you to calculate what is the change in the entropy of the reaction, this is nothing but the sum of the entropies of your product minus sum of the entropies of your reactant. Okay. So what will happen in this case? What is your product? Product is one, right? It is entropy of your AO2, which is actually in the solid phase. Okay, minus entropy of your product. You have two different entropies. Entropy of your component A, which is in the liquid phase, whereas the entropy of your oxygen, which is in the gaseous phase. Right. So initially, when your reactant was in the solid phase, it has converted into your liquid phase. Okay. So if I write down what is my entropy, the change in the entropy of the reaction for my very first reaction, this is what the entropy of your product. So this is the entropy of your AO2, that is your solid, minus entropy of your reactant, that is your A, which is also solid, plus, okay, I'm putting this in bracket, oxygen in the gaseous phase. Okay, so this will be zero, this will be zero, and from here I obtain that delta S of the reaction is basically equal to minus of SO2. Okay. All right. Now, what you need to understand in this case, basically, that this entropy of your component A has now converted into your liquid phase. Okay. So if the entropy has converted into the liquid phase, basically because the melting temperature is lower in this condition. Okay. So what is going to happen? Let us understand this with an example. Okay. So initially, I have my solid as 0.1. I obtained my new liquid. Okay. This is your 10 and this is your 1000, right? So you can ignore your 0.1 as compared to your 1000, right? But you cannot ignore your 10, which is at a much larger scale or a much larger value as compared to your 0.1, right? Your solid phase. Okay. So definitely, you cannot ignore this portion. Okay. So this will be approximately equal to 0. Okay. But your change in the entropy, basically the slope of this line will be nothing but minus SA in the liquid phase minus S of oxygen in the gaseous phase. Okay, this is how you calculate what is the slope of the line. Okay, so I can basically say this is what this is minus. If I take minus common, SA plus SO2. Okay, this is your liquid phase and this is your gaseous phase. Okay, now this entropy is much lower as compared to your first case where you will obtaining just the entropy of your gaseous phase, right? So your M, which is minus delta S. Okay, now this entropy value has basically reduced down, further reduced down. Okay, so if this entropy value is going to further reduce down, then definitely the slope of the line will be further going in the upper direction, right? So you can write this point basically. If the slope of the line we are talking about the oxide line. goes in the upward direction, okay, when it goes in the upward direction, then definitely phase transformation has occurred. Phase transformation has occurred in the reactant side. Okay. All right. So similarly, if I ask you, so this was what? This was your case one, right? Okay. Similarly, if I ask you, what will be your case two? What will be the condition for your case two? That is the line, this oxide line is basically going in the downward direction. How is this possible? Let us see that. Okay. So your case two is basically the line that is going in the downward direction. Okay. Now, what you need to understand, if the slope of the line oxide goes in the upward direction, phase transformation has occurred in your reactant side. Okay. So similarly, if the phase transformation occurs in the product side, definitely the slope of the line will keep on decreasing, right? It will go in the downward direction. Okay. So let me take the same example. Okay. So I have my A plus oxygen. It gives you AO2. Okay, so this is your solid phase. This is your gaseous phase. And this initially was at solid state. Okay. Then on further increase in the temperature, your melting point of AO2 is, in this case, is less than the melting point of A. Okay. So basically, if the melting point of AO2 is less than the melting point of A, on increasing the temperature, basically your oxide will be converted, there will be a phase transformation at the oxide side much faster as compared to the reactant side, right? So what will happen? If I find what is my change in the entropy of this reaction, this is nothing but the entropy of your product, right? S of AO2 minus entropy of your reactant, that is S of A plus S of O2. That is their respective entropies, right? So what will happen? Let us see. Let us see. So if I write down what is my entropy, change in the entropy of the reaction after this transformation has occurred, that is your solid product has now converted into your liquid or molten product. Okay. So if I do so, your delta S reaction, what is this? This is nothing but the entropy of your product, right? So entropy of your AO2 minus entropy of your A plus entropy of your oxygen. Okay. Now this is in the liquid phase, this is in the solid phase, and this is in the gaseous phase. Okay. So I can easily neglect this value and say that it is equal to 0. Okay. So what is the change in the entropy of the reaction? It is nothing but entropy of your AO2 minus entropy of your oxygen, that is in the gaseous phase. Okay. Now understand this. Basically, in the very previous case, we were considering that your AO2 is in the solid state. Right. In the above reaction, you can see that this is your solid, so this will be equal to 0. Similarly, this will be equal to 0. And your delta S of the reaction, this is nothing but minus of SO2, that is in your gaseous state. Okay. But what has happened in this case? Basically, now there's a transformation of your product, right? It has converted from your solid phase to your liquid phase. Now you cannot ignore this value. Okay. So you cannot ignore the value of your entropy in this case. So what will happen? Your delta S reaction. Okay. So basically, the delta S reaction in terms of the entropies of your oxygen, this is a negative value, right? Whereas this is your positive value. So definitely it is going to lower down. Okay, it will still be your negative values because the entropy of your gaseous phase is much higher as compared to the entropy of your liquid phase, right? But their difference will be lowering down. Okay, so if the difference is lowering down, then definitely you can say that since there's the difference is lowering down, so you can say that the value of your delta S reaction, okay, it has become less negative now. It is still negative, but it is now less negative. Okay, so if your delta S is less negative, then it will definitely go in the desired direction as per your case 2. Okay, that is the lines of the oxide line will go in the downward direction. You can write this down over there. The oxide line will go in the downward direction. Okay, so this is the reason why you obtain the change in the slope of some lines. You obtain the change in the slope of some lines at a particular temperature value. Basically, there is a change in the transformation of the phase. Okay, so if the phase transformation occurs from your reactant side, your line is going to go in the upward direction. Whereas if this phase transformation occurs from your product side, the Ellingham diagram will be going, the oxide line will be going in the downward direction. Okay. So with this, we have completed our oxide part. That is covered everything inside your Ellingham diagram. In the then we will be seeing what is your sulfide reactions. What are your sulfide reactions? And based upon that, we are going to generate and develop what is your predominance area diagram. Okay. Thank you.